All right, so let's tackle a very big question. It is question 246. So this question will take some time to solve, and I can guarantee you it's an important question to practice. In this question, we're going to combine many concepts we have seen in the previous chapter, including this chapter. So let's read the question first. So in question 246, an hydro dam produced 100 megawatt of power at a voltage of 10,000 volt. L1, L2, and L3 represent the transmission line, and T1 and T2 the ideal transformer. Ideal transformer means they don't lose power. The transmission line are made of aluminum with a resistivity of 2.7 multiplied by 10 power minus 8 ohm meter and a cross-sectional area of 0.001 meter square. The transmission line L1 and L3 are respectively 0.5 kilometer and 1.5 kilometer long. Given that the ratio of the number of turns from the first transformer is 20, so NS divided by NP is equal to 20, the voltage at the city is 10,000 volt and the power consumed by the city is 80 megawatt. Find the power loss in L2, the length of L2, and the ratio of the number of turns from T2. All right, so there is a lot of material in this question. Let's explain in general terms what all of this means. So first we have a diagram, and now there's a bunch of numbers, but initially the diagram is simply there's a power plant, there's a transformer, two transformers, T1 and T2, there's the city, and there are wire L1, L2, and L3 that connect everything together. So this is obviously a basic simulation of the power loss between the power plant and a city that will be consuming that power, all right? So it's a gross approximation, let's say. Now, the power plant creates energy at a certain voltage. So in this case, it's 100 megawatt of power at 10,000 volt. There's a certain distance between the power plant and the first transformer. What happened here is the transformer will increase the voltage here in order to prevent the power loss in L2. Now, as you will see by the end of this question, L2, even though it does not look on the diagram, is a very long wire. It connects the power plant to a city. In some cases, for example, in Quebec, we supply energy up to some resident in Florida. Well, that's nearly 5,000 kilometers right there. So it's a very big distance, and the job of this transformer is to minimize as much as possible the power loss in this very long wire, all right? So we are given many different value. We are told that the voltage is 10,000 volt at the power plant over here. Now note, there's a power over here of 100 megawatt, which means that there's a certain current. We can calculate the current at this point already. There will be some energy loss in this wire. There will also be some voltage loss. So we got 10,000 volt at the exit of the power plant. There won't be 10,000 volt at the entrance of the first transformer, all right? We are also told that at the city, the voltage is also 10,000 volt, but we have less power, which means we have less current also. So we lost some energy in between the two. We are given some value regarding the resistivity of the wire. So remember that the resistance is equal to the resistivity multiplied by the length of our conductor divided by the area. So we got resistivity of 2.7 multiplied by 10 power minus 8 multiplied by the length divided by the area. The area is 0.001 meter square. So it's 2.7 multiplied by 10 power minus 5 multiplied by the length, okay? So I wrote it that way because we need to calculate R1, R2, and R3. Now, by the way, when I say R1, R2, and R3, I mean R1, the resistance in the first wire, R2, the resistance in the second wire, R3, the resistance in the third wire, and same logic for V1, V2, and V3, okay? Now, once we get to the voltage and current at the transistor, we will use a different notation. This problem is packed with notation. The most important one really is the resistance and current on each of the wire. Once we have these, it's easier to solve the problem. All right, so using this formula, we have already the length of L1, the length of L3. We can find R1 and R3. Simply, R1 is 0.0135 ohm. R3 is 0.0405 ohm. we can already find the current in the first wire using the voltage over here and the power. So remember that power is voltage multiplied by current. So if we want to find the current, well, it's power divided by voltage. So note I1, the current over here, and this is like chapter 6, there's no charge loss or gain. So once you find the current in any of these wire, it is the same throughout the entire wire. So the current at this point has to be the same as the entrance of the first transformer. So I1, the current through the first wire, is equal to the power, and I added the subscript PP, so for power plant, okay? Divided by VPP, it's not volt peak to peak here, it's voltage at the power plant. So this is 100 million divided by 10,000, we get 10,000 amp going through that wire. Note, I've written these values here because eventually I will need more room to write, and these values are really important, all right? So same logic for the current in the third wire. In the third wire, we use the same logic, but we have a lower power. We have 80 million watt divided by 10,000, so we get a current of 8,000 amp here. All right. Now, we would like to know, so in part A, we are asked what is the power loss in L2. Therefore, we would like to know the power loss in L1 and L3 because we can find it right away because we already know the resistance. Note, power loss will be equal to the current square multiplied by the resistance. So the power loss in the first wire, P1, is equal to I1 square multiplied by R1. It is equal to 1.35 megawatt in this case. We do the same type of calculation for P3. By the way, I'm going to erase that part just to make sure you get the full formula over here. So it is equal to I3 square multiplied by R3, and it is equal to 2.6 megawatt. All right, so one thing we need to mention here. All the energy produced is coming from the power plant. And energy in the universe is conserved. So the energy produced by the power plant is equal to the power loss in the first wire, to the plus the power loss in the second wire, plus the power loss in the third wire, plus the energy consumed by the city. Everything even out. So power the power plant is equal to P1, P2, P3, plus a PC, which PC is the power consumed by the city. So basically here, we got 100 megawatt is equal to 1.35 plus P2 plus 2.6 plus 80. So we get the power consumed at on the second power line to be 16 megawatt. All right, so these might be useful. Let's write them down. So P2 especially, we will need that one. So P2 is equal to 16 megawatt. So this is the power loss. P1 is equal to 1.35. Just because I'm running out of space, I'm gonna omit the unit. P3 is equal to 2.6. All right. Now, obviously, the second part is we need to find the length. Once we have the current, power loss, we can find the resistance. Once we can find the resistance, we can find the length. So I will need some more space. Obviously, I'm gonna erase all of this, and this marker is leaving some marks, so I need to use some stuff to clean this. All right, brand new. Okay, so now we know the power on the second power line over here. So we know that P2 is equal to I2 squared multiplied by R2. We want to find the length, L2. Well, using the resistance over here, once we find R2, we can use that term to find the length. Oh, by the way, there's an I over here because it depends on which length we're considering. All right, so we know P2 in this case is equal to 16 megawatts, so 16 multiplied by 10 power 6 is equal to I2 square, which actually we need to find I2, multiplied by R2. All right, so I2 will be useful here. We are given, actually we need to find I2 before we start with this one. My mistake, let's restart that part. All right, so let's have a look at the number of turn on the first transformer. So the first transformer, so I'm gonna call NS1 divided by NP1 is equal to 20. What that means is VP1, VS1 is also equal to 20. Now, because it's an ideal transformer, VP1, and by the way, the subscript 1 is just because I'm talking about the first transformer, IP1 is equal to VS1 multiplied by IS1. All right. We can switch a ratio of current to a ratio of voltage. So VP1 divided by VS1 is equal to IS1 divided by IP1. So that means we take that term, it is equal to that one, is equal to IS1, IP1. Now, by the way, in these type of problem, I highly encourage you to use the current. The reason why, the current is stable in the wire, in each of the 3 wire. The voltage change. There's a voltage drop in each wire, okay? So it's not obvious at all to find the voltage drop on these. Well, it's not obvious. You can do it, but it's a many extra step that's not needed. That's what I mean. All right. So here in this case, let's just identify correctly which one is the current coming out of the transformer and the current coming in. The current coming in the transformer is I1. The current coming out of the transformer of T1 is I2. So we just found that, and I'm going to erase that section on the bottom over here. So we just found that I2 is equal to 20 times I1. There's a mistake there. Actually, let's have a look at this. I think I made a mistake with the formula. Yes, actually, I made a mistake over here. So this is VS1, VP1. Now, the logic here remains the same, it's just that we have to flip them. So IP1, IS1, I2, I1. Okay, this did not make sense. The second wire has to have a very lower voltage, otherwise you will have a much bigger power loss. So I2 is equal to I1 divided by 20. I1 is 10,000, which means that I2 is equal to 500 amp. This value is really useful. Let's write it down. So I2 is equal to 500 amp in this case. All right, so let's go back to the question. We are looking for the length of L2. Okay, so now let's go back to, I'm gonna erase that part. I need again more room. We want to find the length. So P2 is equal to I2 square multiplied by the resistance R2, which is equal to I2 square multiplied by 2.7 multiplied by 10 power minus 5, L2. Okay, we got the power loss here in the second wire. In the, it is 16 megawatts, so 16 multiplied by 10 power 16. The current is 500 square And once we compute everything, we got L2 equal to we got L2 equal to 2,370,370 meter. All right, so that's a very big distance. It's 2,000 kilometer in this case. Very big distance. And there is a significant power loss. 16% of the power is lost in this wire. However, if you are able to send current 2,000 kilometer away, it's worth it. All right, so we just found part B. Now we need to find the ratio of the number of turns from T2. That one is going to be way easier. So for part C, we're looking for an S2 divided by MP2. And we have seen previously that we can link this to IP2 divided by IS2. And this is basically, we're looking at the transformer. The current coming in, so IP2, is equal to I2. And the current coming out is equal to I3. In this case, it's equal to 500 divided by 8,000. So NS2 divided by NP2 is equal to 1 divided by 16. Now, by the way, in some transformer, you might get a value that is always bigger than 1 because basically when you order a transformer, it's your choice which side is your primary or secondary. They will tell you which side is the primary or secondary, but you decide if you want to flip it or not. So it's your choice. In this case, I'm considering the number of turns on the secondary winding divided by the number of turns on the primary winding, and it's 1/16. Now note, we could have solved that problem using the voltage drop everywhere and considering what is the voltage at the entrance, the voltage at the exit, and the voltage drop on each wire, voltage entrance over here and here. But the current is so much nicer to use in these type of problem because it is constant. And I encourage you to use the current to solve these as much as possible. All right, so we are done with question 246. I'm gonna be solving one last question and we will be done with the complete semester basically. So all right, see you in the next video.